Good morning, friends. It gives me immense pleasure to be here for my course Engineering Thermodynamics. This course is related to the mechanical and aeronautical students. I am here to deliver this lecture for aeronautical students. I am Dr. Dwivedi, professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. Today's my topic is property of pure substances. So this I am going to discuss in today's class. These are the topics which I am going to cover today. First is the pure substances, then phase change process, PV and the TS diagram of the phase change process, properties of substances, then a glance on the Esteem Table, properties, relationship, quality of mixture. These are the topics which I am going to take today's. So, what is the pure substance? So, a substance that has fixed chemical composition throughout is called a pure substances, such as water, air, and nitrogen. So, we can say that a substance that has a fixed chemical composition everywhere. If you see one glass, so if you take it is a water, everywhere the water means H2O. So in every point it will be homogeneous and composition of chemical composition will be hydrogen and oxygen. H2O will be everywhere. Same way if you take the air consists of oxygen, nitrogen and some other gases. Everywhere these all things should be same. So this type of substances are called the pure substances, and it is chemically homogeneous. The pure substances are chemically homogeneous, and so a pure substances does not have to be of a single element or compound. So it doesn't mean that your pure substance means only hydrogen or only oxygen. It can be the different elements. A mixture of two or more phases of a pure substance is still a pure substance, and as long as the chemical composition of all phases is same. So this is here very much specified that a mixture of two or more phases. If you see here water, here is a liquid, and if you heat it, you will get here these vapors. This here is the liquid, and these are the vapors. This is also the pure substance, because the chemical composition of the vapor and the chemical composition of the water liquid both are the same. So a mixture of two or more phases of a pure substance is still a pure substance as long as the chemical composition of all phases is the same. So here also you will have H2O, here also you will have H2O. So chemical composition is same. So like this it is also called the pure substances. Now I would like to discuss about the phases. What is the meaning of phases? So here if you see a pure substance may exist in different phases. There are three principal phases. They are solid, liquid, and gas. So pure substance like water, it can be solid like ice, it can be liquid like water, and it can be as a vapor, it is a gas. So pure substance can exist in all the three phases. A substance may have several phases within a principal phase, each with a different molecular structure. So each substance may have several phases within a principal phase, like solid. Inside the solid, there may be some part is liquid, some part is gas. So it is also possible, each with a different molecular structures. Example, I want to give you here that carbon may exist as graphite, it is very hot, and also as a diamond in the solid phase, and ice may exist in 7 different phases at high pressure. Molecular bonds are the strongest in solid and the weakest in the gas. So if you can see that in solid also the same like a carbon, it can exist as a diamond, very hard, very tough, and another is a graphite, it is very smooth, but both are the solid. Same way the ice or carbon dioxide, the in the liquid form, in the solid form, and these all forms are available. So different phase, the same substance can exist in the different phase. So now solid. What is the meaning of the solid? Molecules are arranged in a three-dimensional pattern that is called lattice throughout the solid. The molecules cannot move relative to each other. However, they continually oscillate about their equilibrium. So in the solid, they have the three-dimensional pattern. If you see here, I will just so all will have a proper bonding like this. And here also in this different zones you will have. So a lattice, a three-dimensional pattern will be there, and also the molecular, the molecules cannot move relative to each other. So this molecules, this one, this one, this one, this one, this one, each molecules will not move, but they will vibrate in the same equilibrium condition, move vibrating only in the same condition. So this is the second criteria for the solid. And what is the liquid? The solid, you can see the iron in the, or your aluminum, or your ice, dry ice, these all things comes under the solid. Liquid, the molecular spacing in liquid phase is not much different from that of the solid phase. So these moleculars are in the like this only, generally slightly higher, so little more than the solid, except the molecules are no longer at fixed position. In this, what happened in the solid, their molecules, so here the liquid, what will happen? They will move. They can move from here to here, here to here, here to here, here to here, in a different direction. They are not fixed. They can move to each other. And what is the gas? The molecules are far apart from each other and a molecular order does not exist. So if you see this one, gas, the distance is more and they can move any direction here, there, as per their conditions. And their distance between each molecules are much more than the liquid and the solid. But the liquid and the solid, their molecules are very near. In the solid, they vibrate in the same axis. But in the liquid, it will try to move as per the pressure difference and all. But in the gas, it is abundant, far apart, and there is a very less molecular forces, and they are not having the proper order. So this is for the gas and this is for the solid. So gas molecules move randomly and continually with each other and the walls of the container they are in. Molecules in the gas phase are at a considerably higher energy level than they are in the liquid or the solid. So this you can see that the energy level or the heat or the temperature of this thing is increased. So molecules in the gas phase are at a considerably higher energy level than they are in the liquid or solid phase. Now I will discuss about phase change process of pure substance, how the phase is changing for the different conditions. A process where a pure substance starts as a solid and is heated up at constant pressure until it all becomes gas. Depending on the prevailing pressure, the matter will pass through various phase transformations. So if you take a solid and you heat up, then this solid may become liquid, or this after that it may become the gas, or sometimes solid may become the directly gas. So these depend upon their pressure and other condition. This we will be discussing in due course of time. So what is the solid now? So we have solid, mixed phase of liquid and the solid. Third one is subcooled or compressed liquid, means it is not about to vaporize, means very cold. This I am going to discuss subcooled or compressed liquid. Next is a wet vapor or saturated liquid vapor mixture. The temperature will stop rising until the liquid is completely vaporized. So first one is the solid, next one is the mixture of liquid and the solid. If you give further heat, then sometimes it may be very subcooled or compressed liquid, means they are not going to vaporized. It is in a very low pressure and at a high temperature. Wet vapor, it is a mixture of liquid and the vapor. During making the steam in the boiler, we get like this condition. Next is the superheated vapor, a vapor that is not about to condense, means it is very high temperature, and subcool is in the condensed condition. So here all these five are shown here. This we can see that how the phases are changing place. So here this all this atmospheric pressure P0 here, this is the P0 here. So here this is the system, S is a system, and here we are supplying some heat energy dQ. In the solid case, it is like this. Case 1. Case 2 is mixed phase of liquid and the solid. So in this, here is the solid and here is the liquid. If you give some higher temperature, this piston will move little up, gases will form here. If you give the further this solid will become the purely subcooled liquid, full of liquid here. Further, if you give heat, this liquid, some part of this liquid will change to the gas, and if you give further some additional heat, after when this all liquid is converted to the gas, it is the superheated vapor. So this is the superheated vapor. Okay, so this is the final stage. So from solid here, this is the solid to vapor, how these 5 phases we are able to change. Then only we will phases are changing in this way. So here we can see that phase change process of a pure substance. All these 5 processes are shown here in TV diagram for a heating process of a pure substance. So here this at 1 we have the solid, like if it is a ice. So here it is a solid at 1. At a given pressure, the temperature at which a pure substance start boiling is called the saturation temperature. So here at a given temperature, the pressure at which a pure substance start boiling is called the saturation pressure. So here if you see this point, this is the saturation temperature. Okay, so like this, and at the temperature at which the pressure at which a pure substance start boiling is called the saturation pressure. So the pressure at this point is called the saturation pressure. During a phase change process, pressure and temperature are dependent property. So if you see here, from this liquid to this, from here to here, here is the saturation vapor, and this is the saturated liquid. So from here to here, this P is a function of T. Means if you vary the pressure and the temperature, if you vary the pressure, temperature will also vary. Just I will show you here. It is like this. So this is the pressure and this is the temperature. So if you vary from here, initially it is here, and if you again you increase the temperature, pressure will also. So a fixed, for a fixed pressure there is a fixed temperature, and for the fixed temperature there is a fixed pressure. So between this to this, from liquid to the vapor, this where P and T phase change process, pressure and temperature are dependent property. They are not independent property. So that we have to understand. The critical point is the point at which the liquid and vapor phases are not distinguishable. So if you see here, just I will, how you can get the, if suppose we have one PV diagram like this. So if you see that, so if we draw like this is called the critical top point here. This is called the critical point. And this, how to draw this for each pressure, this is the P1, P2, P3, P4, and this is the specific value. So this we can get like this. So in this case, the whenever phase change from liquid to gas, here in between temperature and pressure remain constant. If you increase the pressure, temperature will also increase in the same ratio as I have shown earlier. So during a phase change process, pressure and temperature are dependent property. The critical point is the point at which liquid and vapor phases are not distinguishable. So in this point, here is the liquid and here is the gas. You cannot, all of a sudden liquid and gas will be same. So you cannot distinguish. That point is called the critical point. So if the temperature is high here, more than this temperature or the pressure is high, then your liquid will be converted to the gas immediately. So the triple point is the point at which the liquid, solid and the vapor phases can exist together on PV or TS diagram. Okay, so this is also very important point that we have to understand. And what is the, so just you see here I am, so it is like this, like this. So this is the triple point. In this is the solid, this is the liquid, and here is the gas. So, and this is called the triple point. So what is this triple point? That the triple point is the point at which the liquid, solid and vapor phases can exist together. So if you see here, if it is the solid here and I am giving the PV diagram. So if I give little heat, so it can directly from solid to gas. So if this is the pressure, this is called the pre-triple point. So if the pressure is less than this, or temperature is less than this pressure, and in this we are giving the heat less than this pressure, so this solid will become the gas. Like if I want to make ice and the pressure is less than this here, ice will not become the water, it will directly become to the gas. But if the pressure is more than this critical pressure or this triple point pressure here, somewhere here, first it will go to the liquid ice, then after that it will go to the heat, this vapor. So solid, liquid and the vapor. But if the pressure is less than this, then directly it will, and if you give the heat, this will go to the gas directly. So this is very important. But in the triple point, all the phases, all the three phases can coexist in the one point. This I have shown you in this diagram. The triple point is the point at which the liquid, solid and the vapor phase can exist together. On PV or TV diagram, these triple phase states form a line called the triple line. And these are the three lines. This is the liquid line, this is the vapor line, and this is the solid line. So this we have to, and here I have given a table, critical and the triple point of water and the oxygen. So if you see the water at atmospheric P atmosphere 218, critical temperature is 643.30, and the triple point is very less pressure, 0.006 atmosphere, and 273.17 means 0.01 degree centigrade. So if this much low temperature if you make it and this much low pressure, your solid, and it will, from solid it will become the gas directly, water also. And if you take the oxygen, it is minus 219 degree centigrade, minus 219 degree centigrade. This will, and this is the 0.01 degree centigrade. So these are the critical point. In critical point, if you see, liquid and the vapor will not be distinguished, all will be same. But in triple point, if it is less than this, as I have explained here, so it is, these 2 points are very important. So the PV and PT are phase change diagram. So vapor dome. So what is the vapor dome? The general shape of a PV diagram for a pure substance is very similar to that of a PV diagram. This you can see, this is called the vapor dome. Okay, this is the vapor dome, and here P and V, here PV diagram, this is the figure. So Here is the critical point, and this is called the vapor dome. The PT or the phase change diagram, pressure and the temperature diagram. This you can see here, triple point, very, very clearly it is distinguished. So this you can see here that substance, it is a P and T diagram, and here this is the substance that expands on freezing. So if it is freezed and if you melt, it will expand. Substance that contract on freezing. Here is the condensation from liquid to vapor and vapor to, it is vaporization. This is the melting, and this is the sublimation. So sublimation means what? If this is the solid and you give some heat, this solid will become to the vapor. This is called the sublimation. And if you even freezing is there and you give some heat, it will melt, and after that it can become the liquid. From liquid it can be vaporized. So here this is the critical point here, and this is the triple point. So the triple point is very, very less, and in the pressure, temperature, the value of is very less. Here is, if it is vaporized and you go towards the liquid, it is called the condensation. From solid to vapor, it causes the sublimation. From solid or freezing to the melting, it is called melting. So these are the few important points. I will also just recommend like this, that two ways from solid phase to vapor phase. This is called phase diagram, since all three phases are separated from each other by three lines. Most pure substances exhibits the same behavior. This you can see here, that most of the pure substances, they will have the triple point, they will have the critical point, they can be vaporized, they can be melted, they can be made the sublimation. So vaporization means from liquid to gas. If you are making, it is called the vaporization. If from vaporization, from vapor to the liquid, it is called the condensation. From solid to the liquid, it is called melting. So this we have to understand, and there is very important here, if this pressure is more than this P triple point, this will follow. If it is here, this will follow melting to liquid, and liquid to vapor. But if it is here, if you can see here, very near to this, it will go solid. It will not, you will not experience melting. It will be liquid little, and then it will go. But if you are below this pressure, here, somewhere here, this is directly, it will be converted from solids to the vapor. So pressure and temperatures are very much important, and that we have to. Here if you see compressed liquid region, this point, this line from here to here is a saturation liquid line, and from here to here it is a saturation vapor line. It is shown here. This is the pressure. So if you initially, the pressure will drop, and as and when it is reaching to the saturated liquid line, pressure and temperature will remain constant. As it is reaching to the saturated vapor line, again pressure and temperature T2 is equal or less than to greater than T1. So here also T1 is equal to constant. T2 is always greater than the this T1. So this, if it is higher, the here also if you see, the pressure is this one, and this is the pressure is this one. So it is compressed liquid region. Here it is fully condensation, it is purely liquid form. As it is reaching here in this point, from here onwards, this liquid is transforming to the vapor slowly, and here full vapor is full liquid is converted to the vapor, and up to here your temperature will remain constant, and this, if you give further heat, the latent heat will increase. So this is a very important diagram. This things we have to understand. One exception is water. Water expands upon freezing. Except water, if you freeze, water will start expanding. And other things, if you freeze it, it start squeezing. Phase change and the triple point. That so here I am discussing about the triple point. So there are two ways that a substance can pass from solid phase to vapor phase. So solid phase to vapor, it melts first into a liquid and subsequently evaporates. So here this you can see, from here freezing to the melting it will become the liquid, and from liquid it will become to the evaporation. It melts first into the liquid and subsequently evaporates. It evaporates directly without melting. So if anything is here, and so from here it will not melt directly, it is become the gas, like camphor, karpur. So if you put a fire here, karpur will not convert to the liquid, it will become the gas. So it evaporates directly without melting it is called the sublimation. The sublimation line separates the solid and the water vapor. This you can see, this is the sublimation line. So this will separate from solid to the liquid or the vapor. This is the vapor. The vaporization line separates the liquid and the vapor region. So if you see here, this is the vaporization line. This vaporization here, this vaporization differentiate between liquid and the vapor. The melting or fusion line separates the solid and the liquid. So the melting or the fusion line, here is melting or the fusion line is here. So this will separates the solid and the liquid. So here is the melting. This is the melting or the fusion. This is the from solid to the liquid. These three lines meet at the triple point. So this vaporization line, and then melting line and sublimation line, these three lines meet at the point, and this point is called the triple point. If P is less than P triple, just you see here, this is the P TP. If this pressure is this P TP, if this pressure PT is less than PT is less than, means somewhere here or here, less than the TP, the solid phase can change directly to a vapor phase. Very important. So if your work area is in this zone, less in this zone, so it will directly convert from solid to the vapor zone. At P is less than PT, the pure substance cannot exist in the liquid phase. So in this range, there will not be liquid. There will be solid or the vapor. No liquid will not be exist. Normally, most of the cases, it will be P is greater than here, this side. P is greater than PTP. The substance melt into a liquid and then evaporate. So from here, solid to the liquid, move like this. Here is a liquid, solid, liquid, and then it is evaporated. Matter like CO2, which has a triple point above 1 atmosphere, sublimate under atmospheric condition, dry ice. So like the CO2, in above the atmospheric also, it will sublimate, and from solid karpur or your CO2, if you just put like this, it will start converting from solid to the vapor. For water as the most common working fluid, we are interested in the liquid and the vapor region only. For the water, we are only interested in this region. Okay. Above 1 atmosphere, sublimate under atmospheric condition. So if for water as the most common working fluid, we are interested in the liquid and the vapor region. Hence, we are mostly interested in boiling and the condensation. So in this phase, we can see that we will be studying about the air and the water, and in this we are very much interested from liquid to this zone, boiling and the condensation. So here it is a condensation, and if you give the heat, it will be boiling, and boiling is called the vaporization. So here we cannot remember all these properties, so we need to use some tables, and these tables are called the property table. For most substances, the relationship among thermodynamic properties are too complex to be expressed by the simple equation. Thus, properties are frequently presented in the form of a table as shown below, and this is called the Esteem Table, and I have shown only for the saturated water. So here if you see subscript F for saturated liquid. If you see here, F for the saturated liquid, G for the saturated vapor. Fg is difference between saturated vapor and the saturated liquid. If you see here, Vf, it is a specific volume for a saturated liquid. And here Vg is a specific volume for saturated vapor. And the difference between Vg minus Vf is equal to, it is called Vfg, is the difference between saturated vapor and the saturated liquid. Another property is internal energy, kilojoule per kg. Here also UF means it is saturated liquid internal energy. Ug is saturated vapor internal energy, and Ug minus Uf is equal to Ufg. If I want to show here in a diagram, this you can see here that if I draw a diagram like this point is F and this point is G. So like this. So if you want to find out for saturated liquid, you have to go in this. Here temperature and pressure is given. So at this temperature, what will be the Vf? This you can directly, you need only one quantity. If you want to find in between either P or T. So 5 degrees centigrade, 100 degrees centigrade, 65, these all things are mentioned here. And from there you can go one by one, like 15 degrees centigrade, you find out Vf. So Vf is this and Vg is this, and this minus this, you will get this. So here it is directly it is mentioned. Same way all the properties we can find out by the help of our tables. So now I will discuss about properties and their relationship, because we have to find out by observing one parameter, we can find out the other parameter. So what is the enthalpy? Enthalpy is a property defined as H is equal to U plus PV. U is internal energy and PV is a work done. But if we make it as a specific enthalpy, all the alphabets will be in small letters. So if we divide it by the mass, H by M and by M, this will become here specific enthalpy is equal to specific internal energy plus here work done, specific work done per mass, kilojoule kg per mass. So this unit we have to understand, and we should remember that this is here specific volume here, not the total volume. So enthalpy is a summation of internal energy plus work done. Enthalpy of vaporization or the latent heat. So what is the enthalpy of a vaporization? That is called the latent heat. Represents the amount of energy needed to vaporize a unit mass of saturated liquid at a given temperature or pressure. So if you see here, from here to here, this is the P and this is the V. And if you start boiling, we give some Q here. So from here to here, there will not be any change of temperature and the pressure. So whatever pressure is here, 1 atmosphere and 65 degrees centigrade, from here to here it will be same. But you need to give the heat. That heat which is used from vaporization from liquid to the vapor is called the enthalpy of vaporization, and this is also called the latent heat. So represents the amount of energy needed to vaporize a unit mass of saturated liquid at a given temperature or a pressure. It decreases as the temperature or pressure increases. So the value of, just you can see the statement, this one. It decreases as the temperature of the pressure increases and becomes zero at the critical point. So this range, if you see here, it is a P1 and if this is the P2 and this is the P3. So as you go, this heat is reducing. Here is more. If you see here, it is very much little reduced, further reduced, and at here, at the triple point, it will be zero. This is called the critical point. At the critical point, the latent heat is zero. So next is, what is the meaning of saturated liquid vapor mixture? So during vaporization, a mixture of part liquid, part vapor exists. So if you see here, in this, this is the liquid line and this is the vapor line. In between, if you see, there is a mixture of vapor and mixture of the liquid. Some part is liquid and some part is vapor. So during vaporization, a mixture of part liquid, part vapor exists. To analyze this mixture, we need to know the proportion of the liquid and the vapor in the mixture. So if you see here, here is a pure liquid, here is the pure vapor. So if we are between here, so how much is the vapor and how much is the liquid? That we have to find out. And that is called the quality of the steam or quality of the vapor. So this quality X is equal to defined as the ratio of the mass of the vapor and total mass. So if you see here at 1, 2, 3, you have the different quality X. So the quality X is the mass of the vapor divided by the total mass. And this total mass is equal to total mass of the liquid plus total mass of the vapor. Liquid is given the subscript F and the vapor is G. So it is the summation of MF plus Mg, and this X is called the quality of the vapor. Saturated liquid vapor mixture is treated as a combination of two subsystems, two phases. The properties of the mixture are the average properties of the saturated liquid vapor mixture. So if we tell the quality, or it is also called the dryness fraction. Another name of this quality is dryness fraction. So this saturated liquid vapor mixture is treated as a combination of two subsystems, two phases. The properties of the mixture are the average property of the saturated liquid vapor mixture. So we take average, not this only one. quality or the dryness fraction of the steam. This we can see here the total volume of this system is the total volume of the liquid and the total volume of the vapor. Here the red and this is the blue. So this V is equal to Vf plus Vg. Next is this V. This volume is equal to mass into specific volume of average. So this is the empty total. V average is equal to here mf into Vf plus mg into Vg. So now this mf is equal to what? mf is equal to saturated liquid. So this mf is equal to total mass minus vapor mass. So here we can write that mt V average is equal to mt minus mg Vf plus mg Vg. So here mf we can write mt minus mg. So in this mf we have put here mt minus mg into Vf. Now if we divide both sides by the t, so this mt, so if we divide here mt, here also mt, and here also mt. So what we get, this empty cancel, we will get average specific volume is equal to this cancel out. So here we will get 1 minus mg by mt is equal to x. We have defined already. So here 1 minus x into Vf plus mg by m1 is equal to again x into Vg. mg by m is equal to x always. So we got here that V specific volume is equal to 1 minus x into Vf plus x into Vg. So this equation we have got, and from here we can find out that F, this V average is equal to Vf plus x Vfg. So Vfg, Vf is what? This is the Vf, and here is a Vg, and here if you see this is called here Vfg because Vg minus Vf, Vg minus Vf. So if you take out Vf here, so we will get V average is equal to Vf plus x Vfg, and this Vfg you can get directly in the table. So V average is equal to Vf means volume at here plus volume at here into x. So from here you can find out very easily, and this is the derivation for a quality or the dryness fraction of the system. So this x dryness fraction is equal to V average minus Vf divided by Vfg, and this what is the Vfg? It is a Vg minus Vf. So we can find out in this way the value of dryness fraction x if you know the volume. Same thing we can do by the help of other parameters like internal energy and all. So here U average is equal to Uf plus x Ufg. So H average is equal to Hf plus x Fg. On a general, it can be summarized as Y average is equal to Yf plus x Yfg. Note that this value of x fall between 0 to 1. So this Yf will be less than or equal to Y average, and this is will be less than equal to Yg. So this Y average will be in between Yg, if this is the Yg and here is the Yf. So this real average in the point will be between this and this. So this we have to understand, and we have to verify during our solution that these things are working properly. Note, pressure and temperatures are dependent in the saturated mixture region. So here this, we can see here, this is the figure here. So here we have the gas, here we have the liquid. So gas is x mg by m, and in the liquid it is 1 minus x, it is mf by m. So that is the difference. We have to very much carefully that gas, how much percentage of gas. If it is 100%, there will be full gas. And if it is 0, there will not be any gas. So x is equal to mg by m, and 1 minus x is equal to mf by m. This is a steam table for the superheated vapor. In this superheated, your pressure and temperature both have to be, if you see here that P and V. So here above this is a superheated zone. Here is the saturated zone. So if you are going above, you need P and T both. True. And but in between this, you need only P or T with X. Any one of this and this dryness fraction you are required. So that we have to take care that if you are above this saturation point, we need two independent properties. Anyone, P, V, T, any two are required to designate the state. Here I have given here, just you can see here that at P is equal to 10 kilopascal and temperature is 45.81 degrees centigrade. Here is a 50 kilopascal, and this means temperature and pressure has to be given. Then only you can find out the correct value of different parameters. Compressed liquid. So in this, I think if I show like this area is called the compressed liquid area. So if it is in this zone, you have to use this table. If it is in this zone, you have to use this superheated. And then if it is here, it is a vapor, and that thing you have to use. So in the next class, I am going to discuss about introduction to thermodynamics, branches of thermodynamics, equilibrium, systems and types, approaches of thermodynamics. These are the references which I have taken from P.K. Nag, Engineering Thermodynamics. Also, I have referred the NPTEL lecture from Dr. Mishra and Dr. Soman. So these things are. Any questions you are welcome to ask. Thank you very much. Please do like and subscribe this channel. Thank you very much for joining.
Like, share and subscribe. Hit the bell icon for more updates.